CLion a cross-platform IDE for C and C++. Download now.
First of all, thank you all for choosing this talk. There are many great talks here. Exciting to see so many faces. And I'm excited to be here. It's my first time in ACCU, so let's hope it's going to be great for you as well. And we're going to talk about Python. Who's excited to hear about Python in the C++ convention? Almost everyone? What are you doing here if you're not excited about Python? And if we are talking about Python, I create many of those. The images that you can generate with LLMs now, they're amazing. So I use them for my PowerPoints, I use them for my YouTube channel, I use them everywhere. The quality of those things and the easiness of the prompts are amazing. And they are Python powered, basically C++ and Python powered together. And we're going to talk a lot about those combinations of C++ and Python and how it happens and helps you in your life. So this section, I call it shameless self-promoting. Bear with me. I'm Alex. I have more than 70 years of system programming. I worked in many system programming fields, from medical fields to defense fields. And basically, most of the time, I work with C++ on huge systems. Right now, I'm working in a company called Speed Data, where we're going to be basically the next big thing in big data. We are creating a new CPU that will accelerate your big data analytics. And the most exciting part is that the actual chips has arrived this Sunday. Those are the first chips. If you would like to talk with me about these chips, what they are doing, please do it after this talk. I will be happy to do that. More about me, I'm very active in LinkedIn. I talk about C++ a lot, Python sometimes. I have a blog, CPP Next. I have a YouTube channel. Please subscribe and look at the things that I have there. I'm a committee member for C++. And last news from yesterday, I'm going to be a keynote speaker at CPP North. So if you're in Canada, it's going to be a new talk. I still don't know what it's going to be, but it's going to be great. I promise you that. Okay, so now we're starting the actual talk, and we will start with a survey. Please scan this. Okay, so that's pretty good. You can see that if you're using C++, your second most used language is Python. It's not C. It's almost always Python. And this is pretty great, because before I started writing this talk, I decided to do this on LinkedIn as well. And I had almost 600 people replying to this survey. And as you can see here, 64% of 600 people are using Python. They're saying they're using Python as the second language. It's not a competition. You can actually say C++/Python. That's going to be the actual thing, not C++/C. And then I remembered, I already saw that survey somewhere. And this survey is basically something that ISO survey is doing almost every year. They're asking which languages do C++ developers use. And as you can see here, they had 1,225 people answering, and Python is the first language. 72% of those people are using Python as the second language. This is pretty amazing. Now, the question we have to raise is, why C++? In my opinion, it's a silly, ridiculous question. We love C++ because it's C++, and it does amazing things. And we're in a C++ conference, of course. But why Python? Why do so many developers use Python as the second language? Fast development. You can prototype it easily. You can do a lot of things with it. You can develop algorithms in a very easy way. The code is almost self-writable and very easy to read it as well. So if your algorithmic team is writing something, it's easy to do that. You don't have to, you don't have to even compile the language because it's interpreted. Because the language is interpreted, you can create blocks and use Jupyter Notebook, for example, and just work on the nodes that you need. You ran something, it's in the state of the notebook, and then you're just working on something that you need to work on without compiling all the time, without wasting time. And this is a great tool. This is why it's such a great tool for AI tools. When you're developing a new network, you want to do exactly what you want to do. You don't want to compile all the time. You don't want to do those things. And Python gives you everything. Now, because we're in the C++ conference, I wanted to show you with time how C++ became more and more similar to Python. The syntax is very similar now in some cases. So as you know, in Python, we have the print with a formatted string. We can just format it in an easy way. We have a tuple here, and we have another number here, and everything is formatted in place. We got a nice string. In C++, we can do the same. So with FMT, you can do it. It's looked almost the same like in Python. It's an older version, looked exactly the same. But you have the same formatted string that happens for you. In C++23, you have print, but I just wanted to show you something that you can use even now if you have the ability. Just download FMT. You will never go back to cout. In Python, you have a very easy way to print out containers. So here we have a container of a list of numbers, and we have a dictionary of numbers, and they are printed out, formatted, exactly as we wanted. In C++, again, with fmtlib or print, we can do it very easily. Now we are having here an array of numbers and an unordered map of numbers, and they are formatted the same way as before, which is pretty great. In Python, it was really easy to return tuples as output parameters, or basically return. And to do it, you always had the unpacking of the parameters, unpacking of the tuple. You use the function, provided the parameters, and then it unpacked the tuple itself into the parameters. Then you could print it. In C++, since C++17, you have structural bindings, which looks almost exactly the same. You just have to use the auto and the brackets around the parameters that you want to unpack. It takes the tuple out, unpacks it for you, and you can use the parameters. So we are formatting the string with a tuple and with a parameter, and we get exactly the same result as in Python. And the syntax is really similar. In Python, we can run on a container with a for each loop. Of course, everyone here already know about for each since C++11, right? I guess quiet means that yes. But in Python, you could enumerate. And this is a great thing you can do. You can do a for each loop, and then you get the value and the index of that value inside the container. Since C++20, you can do almost exactly the same thing in C++. So you can initialize a value inside your for loop. I will reside only inside the for loop. You can do the print, and you can increase I inside the for loop as well. Then you get exactly the same thing as you wanted in C++. And of course, I wanted to show you the print here as well, since C++23. Now, we can do even better than that. We can create our own enumeration function. Since C++23, we have generators. Generators is a great way to create coroutines and generate data as we go. So here in this example, I'm creating a very simple generator that takes any container, creates an index, iterates over the container, and co-yields with a tuple. It returns the tuple with the index and the value. Then when we're using it inside the loop, a for loop, the for each loop, we are just using enumerate, and we are unpacking it with structural binding. And it looks very similar to Python now, almost exactly the same. But that's C++23. I just wanted to show you that you could do it with lambdas, which is like generators for pool people. And you can do it with C++17. So you're creating a lambda, you're providing a new member to the lambda, which is initialized to 0. Then you're providing the container. The lambda must be mutable because you're changing its inner state all the time. Then we're creating the return value. The return value will be an optional of stud tuple with I and the container in I index, or a null opt. Then we're iterating over I and returning it. So each time we're calling this lambda, we will get an optional of a tuple or nothing. It's a little bit more complicated to use. So here we're using it with auto, we're using enumerate A, then we're telling it while we have a value, please iterate over it. Then we're using an asterisk to unpack the values into structural bindings. And we have almost exactly the same generator as before, but this is much weaker. You have to understand it. You have to initialize it all the time. You have to do more things with it. If you have access to C++23, generators are great tools. In Python, we could ignore values that are returning from a function in an easy way with an underline. In C++, we could do it as well, but it looks cluttered. You have to use stdignore. Whoever used stdignore here? One person, two people. Stdignore is with us since C++11, and almost no one heard about it. It's just a great thing that takes any parameter and ignores it, does nothing with it. So when you're using tie, you're basically saying the first two return things from the tuple are useless for me. Don't do anything, just create our value parameters with them and ignore them. And then we have only seeder that we can use. Since C++26, we have the same underline. We have a structural binding with underline, and it looks much, much better. It looks like Python. Again, we're becoming to a state that the syntax of C++ looks like Python, in my opinion. In Python, it's really easy to do things that are program-oriented, functional programming oriented. I'm sorry for that. Functional programming oriented. And you can use your loop inside the loop to create a list. Here you can see that we're creating a new list from a list that is created inside that list of 20 values. We're filtering it out with values that are larger than 5 and smaller than 9. And that's it. It's one liner that does a lot of work for you. In C++, you can do it now with C++20 because you have ranges. Ranges are very good for functional programming. So let's ignore lines 42 to 45 because it's just a way to do random numbers in C++. Then we're creating a range for each, which fills the number out with the distributed generator that we are creating for a uniform real numbers. And then we're using a filter on that range inside a print. That means we are printing the numbers as they are created. And we're using the same filter. And the feel of that is almost as if you're using Python. We can do more wonderful things with ranges. And let's just say this slide is problematic because views are busted. They are nice to use for this kind of little stuff. But if you forget that views are basically views and you don't have the actual values at your state and someone can delete them or they can be removed, you're in a big problem. But for this example, this is great. We're creating a function that uses odd. It means it will return true if the number is odd. Then it's a one-liner to create a list of numbers, a view of numbers from 1 to 30 that are pushed through the filter. Then we're taking just 10 numbers from that and we're reversing it in the same time. This is a one line that used to be almost 20 lines of code in C++17. This is a big change. And it looks, in my opinion, it's readable and it's easier to maintain. You just need to be very careful with what you're using. So if C++ is becoming more like Python, and a lot of us are using Python, why can't we just use Python? Why do we need C++? And the reason for that is the biggest plus of Python language is its biggest downfall. It's an interpreted language. And that means it's slow. And we need things to run fast. Another thing is it's a dynamic language. If it's a dynamic language, it's much easier for people to make mistakes. And mistakes they make a lot. Now, not everything is bad. But let's talk about the problems that we may create when we are using a dynamic language. For example, be with me right here. We have created a function that just adds 1 to a number. Then we are using it inside the print. What's the problem here? No return. But because it's an interpreted language, if you haven't used the function, or if it's used somewhere inside your code base, it will take you a long time to get it that you didn't have a return. Here is a toy example, so it's easy. Now we return the return here, but the foo function has only one parameter. Then inside the main, we have b that is 10, the same, like the b that we are using in the foo function is the same name of the variable. And then we are printing. Will this work? Yes, it will work because Python takes all parameters from global scope from the function and says, if I have the same name, I will use it. Think about if you are adding new parameters to your function or removing parameters and forget to delete it from somewhere inside your function code, and you have it the same name, and probably you will have the same name in the global scope, you will have a bug that will be very, very hard to find. Let's look at another function. So here we have foo and bar. Inside bar function, we are adding or basically appending lists. That means that we think that A is a list to be appended to. So if we are using foo, everything is fine. But if we are using bar like this, it will fail because 10 is not a list. Who knows what is this is? What is this number? Anyone? This is max uint 32. And we have our favorite foo function that receives 2 parameters and adding them together. And then we're using foo with what is this and 1. What will be the return? What will be printed out? 6 in the end. So Python, we as C++ programmers, when we think about max uint, we think if we will add 1 to it, it will wrap around and it will become 0. In Python, it's a dynamic language. So it says, you are telling me it's a number, it's max uint, but you are adding to it, so I will expand it. Right now, it's 64 bits. It just expanded it for you without asking. We also sometimes like to work with bits. In Python, there is a function that gives you a binary object, and it gives you bits. But if we would look at the type, we will see that the bit class is just string. So it's not actually bits. We're using here a lot of memory for it, and it is slower than we expected. But as I said, not everything is bad. As Python is progressing, it's becoming better and better. And I want to show you a couple of tools that you can use to make your Python code better. Since Python 10, we have typing. That means right now you can write into a function, you can define which type the parameters are and which types are the returns that you're expecting to have. So in this function, we are saying that A and B have to be integers, and the return type must be integer. That means we want a return here. If we will use it, like in line 7 with float, we will get a nice warning that says, I expected an integer, but I got float. If we will forget the return type, we will get a nice warning as well that tells you, hey, I expected you to return an integer, but you're not returning anything here. So please know that. Since Python 12, we got even better things. We have generic functions. So right now, let's look at line 3. In line 3, we're creating a function that uses generic type t, almost like in the C++. We're saying that generic type t can be only integer or a string. And then we're saying that the parameters to the function a is a list of t's, and b is of t type. Then we're expecting the return type to be list of t's. Because we know that a is supposed to be a list, we can use append on it almost safely, and append b to it because it's of type t as well. Then we're returning the list, and everything's supposed to be fine. So in line 8, when we use it with foo, a list of 1 and 2 as a string, and then we're appending 3 to it, everything is fine. But if we will try to append floating point to it, it will tell you, I was expecting something to be an integer or a string, but I got a float instead. So this function is faulty. Please look at it. Please try to do something with it. Another thing we got in Python 12 is the type keyword. The type keyword is like using in C++. It basically says that we have a type u that is templated on t, and t is and u is a list of this t type, or a tuple of this t type, tuple with as many parameters as we want. Then we can define a function, and it's easier to write that this function is generic on u, and it returns the list of u's. Then we're returning a list of u's because a is of type u. So it can be a list or it can be a tuple. In line 10, we're using foo with a list of floats, which is fine. In line 11, we're using foo with a tuple of floats, which is fine as well. And we will return a list of u's. But it's not bulletproof. If you will use a float here, you will get a nice warning. And again, it's a warning. So what can we do with it? If we get warnings, you have wonderful tools in Python, for Python basically, that gives you the ability to lint and type check. If you're actually using typing in your system before distributing the code, or if you're using it in your CI, you must run MyPy. MyPy is a type checker. It's a very strong type checker that will actually produce an error in your CI when you are running. And this thing helps you to save time on debugging like crazy. Python, dynamic language, if you know what you're doing, it can save you a lot and lots of time. So here's how you use it. It's a very simple way, and I used Windows. I'm sorry for that. I almost never do that, but it's here. It's here forever. So you just say MyPy, you say the file. Here, because we are using the typing system, we need to provide something that it's a new generic thing, and we need to check for it. And you will get nice error messages, and your CI will fail. It tells you that you have actual errors that you need to check, not warnings in your IDE. But type checking is not good enough. Sometimes you need actual linters. And in C++ conference, if you will not mention Rust, you will be scaled, right? So rough is a linter, very fast linter that is written in Rust. I said it. And it makes things that the type checkers cannot define and cannot find, linters do find them. So here it tells you that you have a problem, that you cannot use this operator on what you defined it for, something that that MyPy and the type checker could not do. So if you're using, always use MyPy, then use linters, and you will be safe. Many problems will just go away. You will not need to debug them because you will have the errors. Another tool that is written in Rust for Python is RIP. So who uses pip? Almost everyone. Whoever used Conda? What do you think about calendar resolution? How slow is it? How slow is pip? You have RIP. So RIP is a fast thing that does the resolution for pip, and it works much faster than pip. And I had the demonstration here, but it doesn't work. Believe me, it works faster. Yeah, the bar checker belt. But if you want an actual thing that actually catching a lot of trending right now, and it's used more and more and gets a lot of support, it's UV. It's much better than RIP. It's much faster than RIP, and you can actually see the performance here. So if PIP takes you 4.63 seconds, UV takes 0.06 seconds to do the same resolution. That's amazing. That's saving a lot of time when you're using Python. And if you have the ability, move to UV. I'm moving my system, it works to UV right now, and it's magical. Like, it's saving us a lot and lots of time. If you want to learn more about UV, you can just count this. Now, let's talk about performance. Everything is fine and dandy. It's an interpreted language, which is slow, which can be very dangerous. We found ways to do it a little bit safer, but performance-wise, it's getting better as well. So the newer versions of Python are becoming faster and faster. It's not fast as C++, but it's not as slow as it used to be. I didn't find a nice graph for Python 13 and for Python 3.12 and 3.13, but they are faster, much faster. Now, to understand more about Python performance, we tend to think that Python, you don't have to understand what you're doing. So it's an easy language. You don't have to understand. You just write things, and they're working. But you can make your Python code faster and better if you understand the internals. Here we have an example of two very simple functions. We have a very long list in Python. The first function takes the list and sums it up in a for loop. The second function uses the built-in function sum. Then we're running it for 100,000 times. Which function do you think will be faster? Which one? 2. Everyone else agree? Great. So that's good. It took for loop 266 seconds, and it took sum 64 seconds. Why is that? Sum function is a built-in function that is written in C, basically. So, and it knows more about your collections and more about your arrays than it can do more performance-wise for you. For loops in the interpreted languages are very costly. So try to use built-in function for those things, if you can, of course. But we can do even better than that. Who ever used NumPy here? Great audience. So here we are doing almost the same thing, but we are creating a NumPy array, a very big NumPy array, and then we're using NumPy to sum it up. And it takes 3 seconds. That's 19 times faster than the sum function. That's a lot. And if you can use NumPy in your base code, go for it. It's really easy to use, but you have to understand it as well. Why is NumPy so fast? NumPy is written in C and C++, and it is binded to Python. It's a very easy abstraction over multidimensional arrays, and it has a lot of functionality. So if you need something, you can always look at NumPy for this kind of functionality of summing and doing multiplication on arrays. Mathematically, it's amazing. As I said, you need to understand how NumPy works as well. So NumPy has a very nice API that says, all my function can work with NDArray-like. NDArray-like is almost everything. So a list in Python is NDArray-like as well. Here we have two functions, that our sum function that we already used, and we have npsum, function 3, but we are providing it a normal Python list. Then we are running it for 50,000 times. Which one will be faster this time? Function 2? 3 or 2? 3. Okay. Function 2 is faster. Anyone can think about why function 2 is faster, even though that NumPy is written with vertices and everything, and it's still slower? So someone in the audience, it was you? Someone in the audience said that you have to do copies. And yes, you have to do a lot of copying. Each time you're calling that function, it is taking the Pythonic list, it's creating a copy into C memory with an ND array doing the work on it, and then copy it back to Python. That's a huge, huge overhead. And if you are using NumPy, you have to understand those vulnerabilities, I would say, that if you use it, it doesn't mean it will be faster. You have to know and understand how to use it to make it really fast. Some takeaways from what we already saw: always use things that are already implemented. Python is a rich language that has a lot of open source things, and you can just use them out of the box and get performance, because a lot of things now are just binded to Python. So a lot of things behind the scenes work with C, C++, and a lot of good packages are now written in Rust as well. Use the APIs as they were developed to be used. Don't abuse it. If it says NDRA-like, understand what it means if you use an actual Pythonic object on something that expects to be a fixed point array in C++ memory. That will save you a lot of time, literally. More open source models, and this one of my, I don't know, my loved model, like PyTorch. It's almost the same as NumPy, but it's meant to work for AI. If you want to play with AI and understand how networks are built, it's a great tool to do it for you. The core language, the core of PyTorch is written in C++ and in CUDA. It's really easy to use CUDA from Python with PyTorch. It's easy to understand how things work, and basically to do mathematical equations and operation with it instead of NumPy as well. Because you can, if you have GPUs on your computers, it will do much better. So here we have an example of how to use PyTorch for tensor multiplication. We have huge tensors here, and we are multiplying them for 1,000 times, and now we're multiplying them on the CPU. And it takes it 40 seconds for these huge tensors to be multiplied 1,000 times. That's pretty impressive. As I mentioned, it's really easy with PyTorch to use the CUDA device, or basically the GPU. So here it's almost the same functionality, but we are saying all the tensors are already allocated on the GPU. And then we're doing the same multiplication 1,000 times, and it took it 4 milliseconds. Because it did everything. And as you know, GPUs are very good in tensor multiplication. Now, again, we have to understand how things work. So here we have almost the same functionality, but here I'm doing the full round trip. If I need the data in my CPU, after it was multiplied in the GPU, I need to say, please bring it to the CPU. And just because I'm doing this round trip, it takes it 31 seconds to do the same operation for 100 times, not 1,000 times, 100 times. The overhead of copying through PCI Express is really costly. And it depends on the type of card that you have. If you have PCI Express 3, 4, or 5, it may get a little bit faster or slower. I will just mention all this benchmarking was done on the RTX 480 Ti that I have on my machine at home. So that's what we see here. Here I just wanted to show you how easy it is to create an actual network with PyTorch. You have a lot of tools to do it. So this is a network that whoever heard about Amnist? Yes. So Amnist is a very simple AI database that helps you find out if something is a shoe or a hat. This network is basically saying if something is a shoe, a hat, or a shirt. But again, everything is already implemented in PyTorch. You can just play with it. And if you're really interested about how things work in AI, how can you make networks? What does it mean to train a network? To do it in PyTorch is a breeze. And I really, really recommend you to use PyTorch for that learning at home maybe, or if you're using it at work, that's even better. Okay. As we said, we need to try to use all the open source that we have in Python. But sometimes it's not good enough. Sometimes we need to create our own libraries or our own bindings for Python. How can we do it? Let's say that we have this amazing function that our algorithmic team needs to be like that and needs to run in C++ because the performance here is amazing. And I need you all to sign an NDA form after this function. It's like, don't tell about it to anyone, it's proprietary. So luckily for us, our algorithmic team can get the binding for it in a pretty easy way. Let's not forget that Python is basically a C program. One of the interpreters is written in C and it's called CPython. It's not the only interpreter out there, but it's the most used one. We have PyPy as well. It's much faster, it's newer, but it doesn't have all the functionality yet. So the most common usage is CPython. And because Python is just a C program, we can write SO for them, and then we can just use plugins. If we would look at how CPython looks as a schema, we would see something like that. We have a CPython core, we have an interpreter that creates and maintains the state of all Py objects. What is a Py object? Everything in Python is a Py object. All the code that is written in CPython, using Py object. If you are defining a number, it's a Py object. If you're defining a class, it's a Py object. Everything is a Py object. You have your script, so the program is interpreting the script. It's reading the data, it's interpreting it, maintaining the state, communicates with the Py objects, and outputs the data out. And because we can extend it, we can just create extensions. And to create the extension, CPython gives you python.h file. It's the Python API. Basically, you can do and see all the extensions and all the functionality that you have in Python inside python.h. Afterwards, if we are already using the Python, we can create an SO file and attach it. So if we would look at it, if we are creating a new SO file to the Python, we're creating a Py object from that SO file that is managed by CPython core, interpreter and core. It's pretty easy. Now let's look, after I explain how easy it's supposed to be, let's look what we have to do to actually create it. So here we have our function that is written in C. Then we have to wrap this function in a Python implementation, a CPython implementation. So this implementation is receiving a Py object called self, because all Python function receives self as the first parameter. And then another Py object for arguments. This Py object for arguments, we know in this case that we have two integers. So we need to parse those two integers out of the arguments. And then we can actually call the C function inside the Python wrapper. After we call the C function inside the Python wrapper, we can return it as a Python float number. That's the first step. We're not done. Then we have to create methods. We have to say that this function is part of methods that will be used in this module. We will get to the module soon. So we are defining it. Each function has to be defined with the name that it will be called inside Python, the actual function pointer that will be called in C, and description and met var args. Then you have to have a sentinel. It's just how it is for Python, for CPython. Afterwards, we need to create a struct that defines our module. Everything in Python is modules in the end. So we are creating this struct. We are saying that PyModule def init. That's something that we always have to say. We are giving this module a name. We're saying what this module will do. We're saying it's a global state module, and it will use those methods that we created beforehand. This function is really important. We have to create it, and it's called init module, foo module. This function is basically the thing that when you're importing a Python module, those functions are called in CPython. So you're saying when this module is imported, we will create a new module called foo module from the struct that we have created beforehand. We're not done yet. We need to create a setup file. Because we are creating an extension, we need to say, hey, we have a new module with an extension for it. And those are the source files that it will use. We need to then to say, here's the setup method. It will be used for foo method. And the extension module for this method is the module that we created before. And I don't know about you, but I'm a lazy guy. That's too much work for one function. We're in luck. People thought about it and said, yeah, that's too much work for one function. So we created many different binding tools. And during this talk, we will talk about a couple binding tools that you may use. We will cover PyBind 11, which is a very simple tool to use, but it's a static binding thing that will always communicate from C++ to Python. That means you write something with PyBindings, and then you can load it into your Python code. I will mention Boost Python. We will not talk a lot about it. I will cover Cython, which is very, very rich language that lets you bind from Python to C++ and from C++ to Python. It goes both ways. I don't know why, but people are really scared of that code. In my opinion, the code is almost Python-like, almost no difference, but people tend not to use it. And the last thing that we will talk about is CPPYY. Whoever heard about CPPYY here? One person. So you're in for a treat. CPPYY is amazing, amazing. It's dynamic binding. It means that you don't have to compile, but we will get to that soon. Now, how do you need to write your bindings with PyBind 11? So the most important part is to include PyBind 11 in your code. Then we're just using a namespace PyBind 11. Creating our function. This time I noted that it should be C++ and not C. And then we're using a macro. Yes, macros are evil, but in this case, they're making our life much easier. We are providing the macro the name of the model that we will use, and M. Then we're creating documentation for that model. Then we're creating a define for a function that we're saying this function is foo. We will call a function pointer for foo. We're saying how this function, what it does, documentation again. We have the Python arguments that we are providing A and B from the function itself, and that's it. That's it. Well, you don't have to do the loops anymore. You can just use the PyBind, and that's it. Because we're using PyBind 11 and not CPython, we can use a normal build system as well. So if you want to incorporate it with CMake, you can do that. In this example, we're saying that we are finding a package called PyBind 11 because we need to use it. Then we're just adding a library because we're building a library in the end that will be called foomod. And then I think that Conan people are really funny because if you are used Conan, and you use PyBind 11, inside content documentation, it says, if you want to use PyBind, you need to link yourself with PyBind all do not use. And it's called do not use, but they are saying use it. So I don't know. Then we just need to create a simple setup file that just says, okay, I have a new model, no compilation here. You don't need to do anything with it. It's just a Python setup. And then we can use CMake to install it for us. So when we're building the module and linking to it, we already can execute the setup with install from CMake. We're saying, we know where the Python executable is because we included PyBind 11. Then we can just use the Python executable to execute setup.py with install. And that's it. Everything is done from your build system, the integrated build system that you use daily. I think it's much more maintainable and easier, and you will have less boilerplate code. Boost Python, as I mentioned, I will just mention it for a little bit. I think it's even cleaner than PyBind 11. So here we're creating almost the same thing with Boost Python. And all we have to do here is to use another macro and to define a function. It's even cleaner than before, but it's almost the same. You will almost see no difference between those. To use it inside CMake, it's almost the same, but instead of finding PyBind 11, we have to find Boost packages. We have to link to Boost Python 3, and that's it. Until now, I showed you how to do it for simple functions. But what about classes? In the end of the day, we want to write classes, and we want to bind to those classes as well. So here's a nice and simple example. You have a CPP class that uses two functions, foo and bar. When we are using PyBind 11, all we have to do is saying that we're using CPP class model, we're providing M, and then we're using a wrapper that's called PyBind class. And we're saying we're templating it on CPP class. Then we have to create the init function, and basically it's the default constructor for our class. And we're defining the two functions inside our class. It's pretty simple to do it. And again, you must ask yourself, so we are binding to C++ now, or C, so things must be faster, right? Not so much. So in C++, I have run this code 10 million times. The simple function with numbers. And it took it 4.25 milliseconds to run. In pure Python, the same function ran 10 million times, and it ran for 1 second, 1.2 seconds. With CPython, just binding to my C++, it took 1.1. I think it's noise. It's almost the same as Python because there's almost nothing that CPython would contribute to it. With PyBind 11, it took 5.7 seconds. So it was easier to bind, but you paid for it. And why have you paid for it? You have to copy the data from Python to C++ and from C++ to Python. And because we use the function that is so small and we use it 10 million times, we always copy it from C++ and copy it back to it. So we have a huge overhead. And just as if you are using a CUDA program, you need to use hotspots. So what does it mean? You need to create a lot of data and then process it, instead of processing one integer at a time. If you're already transferring a lot of data to a quicker module, it will do a better job to process all the data, and then it will return it back to you. Different bindings do things a little bit differently. And PyBind, for some reason, I don't know why, they decided to do everything on the heap. So that means they are creating lots and lots of heap memory. They are allocating and deallocating, allocating and deallocating all the time. And that's why it creates an even bigger overhead when you use it. What can we do about it? as I mentioned, we can do batch functions. We need to process a lot of data in the same time. That will make us functionality much, much better if we will use it like that. The binding tools have special tools that will make you run faster. For example, PyBind has something that's called dict. Dict is already a C++ object that the memory resides in Python. So when you use dict, you're already creating something that is inside Python memory. PyBind even provides bindings for NumPy. That means you have something like array T. Array T is a binded ND array from NumPy. So if you want to use a lot of binding with a new package and you want to use something that is faster and quicker, you can use array T. And that means you're already creating a memory that is residing in both places. A very important thing to remember that Python is a garbage collected language. So if you created something in Python and returned it to C++, if Python decides to remove it in the garbage collection, the data is gone. So you need to protect yourself. If you can return things with smart pointers, and when I say smart pointers, shared pointers, that's going to protect you a lot here. Here's an example of how to use it with array T. So we're creating almost the same function here, and we're using array T, which is binded to NumPy. As you can see, the usage here is a little bit more cluttered than before, but in the end of the day, it's not that bad. You're just taking the pointer out of the memory, and then you're iterating over the size, and you're doing your multiplication inside it. And when we look at the times that it takes now, C++, because we use something that is Python binded, it takes it a little bit more time. It takes it 62 milliseconds. But if we are using PyBinding now with this, we will get 1 second. Instead of 5 seconds, it's 5 times faster than before. It's still not C++, but it's much better than before. Forget everything you know and don't use the old binding tools. I just wanted to show you them because you have the ability to use it, but don't. If you really want to bind statically, use Python. It's a rich language that gives you the ability to run both ways. It even gives you the ability to Pythonize your Python code. You just have a Python file, you can tell it, hey, compile it for me. Sometimes it makes your code faster without doing anything. Your Python program will run faster without you even trying to make it faster. And you can do much more with it. So sometimes you need to run Python code from C++. I don't know if any of you had to do something like that. Anyone had to run? So this is the only tool out there that lets you do that. You can actually run the Python interpreter inside your C++ code and run Python code if you need it. Now let's talk about, we already covered it with other binding tools, but here I want to talk about how do we convert and bind from C++ to Python with Python. First step is to create a Python C++ class. So here we have a class inside the namespace that's called important. We have an abstract class with 2 functions and a virtual destructor, which is important. We have a struct real that is inheriting from abstract and implements the 2 functions foo and bar. Afterwards, we need to create a file called pxd. pxd in Python is almost like an H file for C++. That means here we are defining how our implementation would look, how our classes would look, and how our C bindings would look. So here we are saying with cdef extern, we are telling it, we will use everything from import namespace that resides in class.hpp. Bring everything from that namespace to the bindings. Then we're creating cdef cpp class. cdef cpp class, that means we're creating something that is a pure C++ class that we're just defining it, and all the functionality needs to be used from C++ itself, from the C++ file. And we will call it C abstract. And we are telling it we will use important abstract to bind here. Then we are creating the abstract constructor. We are creating the two functions. We are saying those functions are foo and bar. They are with integers. Then we're saying, okay, now we have the real class, so it's still a C++ class, and it inherits from C abstract. We're creating the real constructor, two functions, and that's it. Those are just definitions here. Then we have to create something that actually uses, that we can actually use in Python. So we have to create a Python class here. Here we're cdefing a class. That means that it's a Pythonized way to say this class will be used in Python, but it has C++ things in it, C++ or C objects in it. And we're saying that this class will have a member called creal, and it will use a shared pointer to a creal. After we've finished with all the definitions, we have to create a pyYX file. A pyYX file is a file that contains all the implementation details. Good thing about Python, or a bad thing about Python, it depends how you look at it, it wrapped almost all the standard library for C++. So you have all the standard library, almost all the standard library for your disposal. So here we are saying, from my model, from my pxd file, please import all the C stuff that are defined there. We are importing make shared a null pointer from libc++. And we are also importing the reference. Because asterisk is already taken in Python, who knows what asterisk does in Python? Yes, but it's taken. But it's taken and we cannot use it. So the reference is basically using an asterisk in C. It's requesting to dereference a pointer. Then we have to create an actual class. We have to implement the class. So we are saying cdef class pyreal, the class that we are defined in the pxd file. We're creating a function called cinit. So if you are creating a Python class, if you are creating a new class from it, it will call the init function. If you are creating a cdef class, a Pythonized class, the first thing that will be called, even before the Python objects are starting, will be cinit. So all your C++ definitions needs to be run from the cinit function. It will be called before Python starts running. Then we have the init function that does nothing here. And then we're creating the actual binding to the C++ function. So we are creating a cpdef function. Cpdef means that it's something that will have a pure Python definition, but it will have a C++ definition as well. I will try to compile it and not have just the pure thing for you. Here you can see that we are using dereference, that we are important from operators, and we are saying creal. This is the member that we have created. Get, because we have this operation from a shared pointer. We are saying get, dereferencing it, and using the foo function. That's it. As simple as that. So I have to ask you here. I told you many people are afraid of this syntax. Do you think it's that bad? Raise your hands. Who thinks it's bad? Thank you. No one, for the video, no one thinks it's a bad syntax. Now, to compile it, all you need to do is just run Python. You have to tell it, I want to use Python 3 and not Python 2. I want to tell it, we want to compile it to a C++ file and not to a C file. And the model that we are using, model pyYX. It will create a CPP file and an H file for you if needed. Almost always is just create the CPP file, but if you have an H file, it will create it for you. And then we can incorporate it in a very nice way into a CMake system in our code base that says, okay, we need to find the interpreter and we need to find the development package for Python. We need to add a custom command. A custom command is basically something that we need to run, and it's not a regular thing that we need to run. It's not a regular target. So we are saying this thing will output my model CPP, and it is dependent on those two Python files. And when we will find the myModel CPP, when it will find the two Python files, it will run the Python command for us from CMake. Then after that, we need to add a library. Because we are adding a library and we are using the myModel CPP, myModel CPP will be created only after the add custom command will do its thing. So the add library is basically calling the custom command before it executes itself. And that means that we have already a precompiled file, Python as file for us to use. Afterwards, a very important thing to do with Python is to use the set target properties, and the property is a prefix, and it has to be nothing. Why is that? I showed you the function that initialize the Python module. Python creates this function for you. This function will be created with a module with a name that you gave to the library itself. So if you will add a lib prefix to the library, your Python module will not be loaded. It's a very important step if you're doing that. And then we have our own Python installation function that I already showed, that just installed Python for you, uses setup.py, and that's it. You have all the power here. You can do much more things with regular bindings and in a richer and better way. Now, let's talk about the other way around. If we need something to run in C++ that is written in Python, we can do it as well. So let's say that we don't have the ability, we don't have any package managers, we cannot use it, and we're in a system that doesn't have an internet connection. But on the other hand, we have Python on that system. And on that system, we have, because we have Python, we have the JSON library. And we really need to use the JSON library in our code base. Just a story. So we can do it like that. To define a function that can be used from C++ code in Python, you need to do cdefpublic. Cdefpublic will create a C++ function interface that can actually be loaded and run from your C++ code. And the code is pretty simple because using JSON in Python is pretty simple by itself. Then inside your C++ code, you have to load the Python interpreter into your program. So you're DL opening it into your program. And then you need to initialize Python. So you're saying, right, after I load it myself, I need to do my model, pyinit my model. I need to call that function when something is called in here. And then I need to initialize myself. If something doesn't work, we just need to return or throw from here. But that's it. After that, you can just call the function in. Few words about exceptions. So there's no way for your C++ code and Python code to communicate with exceptions because Python exceptions will not propagate into your C++ code. Will not propagate into your C++ code. But it's really easy to fix. So if you want an exception to be propagated, you just need to create a file with a function that is throwing a C++ exception for you and bind it to Python. So here we have it already. It's just a simple function with a string message. And if you actually need to throw an exception from Python and C++, you are just using the throw binded message and it will propagate all over the system for you. Who ever had a problem with Jill? So Jill is our enemy. We hate it. Jill is a problematic thing. So inside Python, until Python 3.13, and not even that, you have something that's called the global interpreter lock. When you run Python code, you don't have threads. That means each time a Python code, even though you have threads in it, it will try to acquire a Jill. That means only one thread from your program can run at a time. And that makes Python really, really slow. So it restricts us, and we really don't want to use it. We want to break free out of Jill. What can be done? So as I mentioned, in Python 3.13, there is finally PEP 703 got in, but we still don't have a normal Python interpreter that does that without GIL. And I'm not sure when we will have a normal interpreter without bugs that will run Python without GIL at all. Hopefully soon, but until then, with CPython, it's really easy to do that. As always, you will have a lot of boilerplate code, but it's easy. We will not cover that here. With Cython, it's really easy to break free out of GIL. You can just use the no GIL keyword on your functions or inside sectors of your functions. You can just say, this sector of the function, this block, doesn't use GIL. And if we can distribute all the operations into pure C++ code, we can just use C++ threads. So if you are binding a function that uses threads, they're not taking GIL because they're running in one instance of Python. For example, we have an implementation here that we want to use without a GIL. So we have a function that just sums up two numbers. We're defining it in Cython, and we are saying no except and no GIL. This function will not throw an exception, and it should run without a GIL. Then we're creating another function. In this function, we're C-defining three parameters in C memory. We are copying from the two arrays into AI and BI. Then we're creating a block that should run without a GIL, with no GIL. And we're using the function that is running without GIL as well. Then after that block, we need to copy it back to Python. It's a little bit cluttered, but it works. Inside your Python code, after everything is done, you need to import no GIL file that we created. You need to import threading. We're creating 3 lists, and then we're doing a for each for those lists and creating many, many threads with those arguments in them. So if we will print it, we will get it. It's a little bit faster, but have you seen the problem here? I had to copy around data from C++ to Python. What will happen if I will just save myself some time here and inside the no GIL block, I will just copy the add elements result into C index. Will that work in your opinion? Who thinks that it will work? No one. Good. Because we cannot use Python objects inside no GIL. Each Python object needs to be inside a GIL-based runtime. So here, just because I put it inside a block that uses no GIL, it says I cannot do the conversion. I have to be inside the GIL. And that's why we had to write the function the way that we wrote it. And now we got to the actually exciting part here, the dynamic binding. So CPython is a great tool that just runs C++ code inside your Python. It uses Cling. Cling is something that is from Clang, and it's a C++ interpreter. Basically, it reads your code and compiles it as you go. It's pretty neat, and it's really fast. It's really easy to use. A lot of my code base was written in Cython and C types, and now we're starting importing everything into CPython, and it's magical. For example, all you need to do to create a function that we had to work a lot to create with static bindings, all you need to do here is that. You're importing CPython, you're saying cppdef, and you're creating your C++ function inside your Python code. Then you're calling the function from the global scope. And that's it. You call the C++ function from a Python code base. Nothing more. If you want to talk about performance, the performance here is great as well. So if you run this code in C++, I already ran it, it's 4.24 milliseconds. In CPython, the same code runs for 724 milliseconds. It's not even a second. If you remember, with all static bindings with CPython, with everything, it's still slower. But here, it's almost the same as C++. Almost. It's much faster than before. You don't need pre-installed compilers. You don't need to wrap STL like you had to wrap with Cython. Cython, you don't have all STL with you. But here, because CPython is just using your C++, pure C++ code, you could just include whatever you want from STL library, and you can use it. It has full support of templates, which is pretty amazing. Full support of inheritance, and full support of callbacks and lambdas. I will show you all of those. So let's start with the class. We have the abstract class, where we are defining two functions. One of them returns an array of 10 members. Then we have the real class that inherits from the abstract class. We are creating a default constructor. We are creating a foo function that returns an array. That returns an integer. And we have a bar function that returns an array. Just an H file. Inside your Python, you can just do import cppyy, include the file that you just created. It will parse it for you. Then from GBL, the global space from cppyy, you are importing real. And if you will look what real is, it's just a class that is created with cppyy. To actually use it, you have to create a new instance from it. So you're creating real instance, and then just using a full function from it. That's it. If you want to extend it, you want to extend your C++ class, you can do it with a mixing in cppyy. So you want to do an extension inside your C++, inside your Python code from a C++ class, it's really easy to do as well. So here we are including array, which is a standard library thing. We're creating a PyReal class, which will inherit from cppyy GVL abstract that we already created. And then we're re-implementing those functions in Python. But inside the Python function bar, we are using array. We're basically creating and returning a C++ collection from a Python function. To use it, we have to create it with new, with PyReal, and then we're just using foo. As simple as that. I have mentioned that it really supports templates, and even crazy templates like this. So here we have a function that wants you to provide it a callback, or basically a pointer to a function that returns R type and receives U parameters. And then the second parameter list, or a variadic list, is the arguments that will be provided to the function. Inside the function, we are invoking the function pointer with the arguments when we are forwarding it inside it. To use it from cppyy, all you have to do is that. We are importing call-it, the function that we binded, because we just did include somewhere previously. We're creating a Python function called f, but here is the important part. You have to help clean, or basically you have to help the interpreter to understand which types are you using. So here we're saying f is using int, and b is using int, and we're returning float. Then we're just doing the foo function that we already know, and we already created it. And then we're calling it. We're calling a function that is defined in C++ and providing it a pure Python function. And the resolver in C++ in clean knows which function it has to create a prototype for a templated function because we provided the types. And it just goes back and forth with all the languages and all the features that you have in Python and C++, and it's really easy to use. Sometimes you need to use libraries that you didn't write, right? Sometimes you want to use something that is written in C++ and you want to use it inside your Python language, inside your Python code, sorry. So let's write just a small library for us. We're doing an extern C, an H file, and we're creating a function. Then we are including the add file that we created, and we're implementing that function. Afterwards, we are compiling it and creating an SO object. And to use that SO object is easy as well. Again, CPP makes everything easy. CPPYY makes everything easy. You're importing CPPYY, you're including the interface file, the API file for add, and then you're saying, please load the library, add.so that we just created. Then to use the function, nothing special here. You are going to the GBL and you are pulling the full function that was created inside the library that you just loaded into your Python code base and bind it without even writing bindings. But sometimes we don't have SO functions, and sometimes we get just A files. There are a couple of ways to fix that. So one of the ways is just to use Clang and transfer the A file into a shared file. I don't know how many people here have ever done something like that, but it's risky. Or you can just wrap your file, A file, just include it inside a different SO file, and all the symbols will report it in because an A file is just an archive. So if you're creating a new SO file, it will have all the symbols inside it. So it's really easy to use. There's an even easy way to include new file paths, and library paths. If you're using library paths in a different and not standard way, you can just provide it with add include paths, just like providing -i to the compiler, and add library path, which is like using -l to the compiler as well, to the linker. So we will know where to find your include files, and we will know where to find your, yes, Peter? Cling, yes. Cling is the interpreter for C++ in Python. And because we mentioned GIL beforehand, let's mention it again. Even GIL becomes easier with CPPYY. So we have a function that calls threads and goes to sleep. Sorry, it doesn't call threads. It just goes to sleep. Because we have created it with CPPYY, it's a CPPYY object inside GBL. Every object inside GBL has an attribute called release GIL. So if you want to use this object without GIL, all you have to say is just release GIL, and that's it. We already can do it without GIL. Then we're creating a simple Python function, run task, that will run the long task for us, and then we're creating a thread. And those threads will not use GIL. And because we're using everything from C++, they can actually run without GIL. While most features do work in CPPYY, some features do not. And they're not working in CPPYY for a long, long time. And the implementer of CPPYY knows about it, and he had a funny comment about bitfills. It's like, I knew it, this day will come. So if you use bitfields, and here is a simple example of bitfields, we have just a struct with using bitfields with 32-bit struct that using X, Y, Z, and S. And then if we will include the file into CPPYY, and we will create this object, we will see that it's just an object. If we will create a new instance of that object with these parameters, and we will try to print them out, as you can see, you get garbage. Because the Python interpretation of bit fields is not good enough. But there is an easy, almost easy way to fix that. So the interpretation in Python is bad. But because we are using CPPYY, it's really easy to write a C++ function that will return the bit fields for you. The representation of the bytes in the memory is correct. Just the Python doesn't know what to do with it. So if we will write a function that's called 2 bytes with CPPYY, we can just get a normal byte stream that gives you exactly what you wanted. So if we are printing it here, you can see that representation of this is correct. Just to show you how to write this function, it's really simple as well. We're creating a templated function with auto. We're using a size. We're copying a data and re-entry casting it into a char pointer, and then returning the bytes to Python. And for closing notes, use the right tools for the right job. Python is great, but the easy language, it is an easy language, but you can do a lot of bad things with it. If you want to use it, use the right tools. Know the inner things inside the language. If you know the inner things inside your language, you know how, well, you'll probably make less mistakes. Use linters, use type checkers to make yourself safe. Actually use them inside your CIs. Don't just use them like locally on your machines and that's it. That's not good enough. This code needs to fail. Try to Cythonize your code. As I mentioned, if you will try to Cythonize a pure Python code, sometimes it will be faster. Try CPython. If you actually need bindings in your code, CPython is great. It will give you performance and it will give you a lot of power and flexibility. Be aware of threading problems. I don't know when we will have Python without GIL, but that's going to be a very interesting part. And it's going to be interesting to see when the real interpreter without GIL will run, how many bugs it will have. So we are done. That was a lot of information for one talk, I know. Do you have any questions for me?